Good morning, everyone. My name is Khushi from BSc Chemistry Honors second year, and today our chapter is amines. Amines are very important class of nitrogenous compounds which may be regarded as derivative of ammonia, in which one or more hydrogen atoms have been replaced by alkyl or aryl groups. For example, methylamine, dimethylamine, trimethylamine. Classification of amines. Amines are classified as primary, secondary, or tertiary amines according as 1, 2, or 3 hydrogen atoms of ammonia molecule have been replaced by alkyl or allyl groups. Primary amines. These are the derivatives of ammonia in which one hydrogen atom of ammonia has been replaced by alkyl or aryl group. Therefore, they are characterized by the presence of amino group NH2 linked to alkyl or allyl groups R. If R is alkyl, the amine is called aliphatic amine. If R is aryl, the amine is known as aromatic or aryl amine. Amines in which the amino group is attached to an aromatic substituted alkyl group may be called as aryl amines. However, they are quite similar to aliphatic amines. Secondary amines. These are the derivatives of ammonia in which two hydrogen atoms of ammonia have been replaced by alkyl or aryl groups. Therefore, they contain imino group NH linked to two or alkyl groups. If the two alkyl or allyl groups attached to the nitrogen atom are identical, the amines is called simple. If the two groups are different, the amines are termed as mixed. Again, the secondary amine may be purely aliphatic or purely aromatic or mixed aliphatic aromatic depending upon the nature of two groups. Tertiary amines. These are ammonia derivative in which all the three hydrogen atoms of ammonia have been replaced by alkyl or allyl groups. They contain tertiary nitrogen attached to three alkyl or allyl groups like secondary amines. They may be simple, mixed, or purely aliphatic or aromatic or mixed aromatic. For example, trimethylamine, dimethylethylamine, and then dimethylamine. Structure of amine. The structure of amines and bonding in them is similar to that of ammonia. As in that case of ammonia, the nitrogen atom of amines is in the state of sp3 hybridization, so that the hybridized orbital are directed towards the corner of a tetrahedron. Like ammonia, the actual shape of amine is pyramidal. The C and C bond angles are very close to tetrahedral of angle of 109.5 degree. Nomenclature of amines. Aliphatic amines. Aliphatic amines are named as follows. Common name. If the common name, aliphatic amines are named by adding the following word amine to the name of alkyl group or groups present in the molecule. For example, methylamine, N-propylamine, dimethylamine, dimethyl N-butylamine. IUPAC system. In the system, aliphatic primary amines are named as by removing the final E of the name of a parent alkane, adding the suffix amine. For example, methanamine, 2-propionamine, 3-methyl, 1-butynamine. The secondary and tertiary amines are named as nitrogen substituted primary amines. If the secondary and tertiary amines are mixed amines, the longest chain is taken as belonging to primary amine. Sometimes in case of complex amine or amines, they have functional group of higher priority. The compound is named by prefixing the word amino before the name of parent corresponding to the longest possible chain. Aromatic amines. Aryl amines. The simplest aromatic amine is benzene ring NH2. Even though its UPSC name is benzene amine, it is popularly known as aniline. Most of the aryl amines are generally named as derivative of aniline, though some of them are given special names also. For example, N-methyl aniline, N-diethyl P-nitroaniline. Diaryl or triaryl amines. Theirs are named in the same way as aliphatic amines, either by writing the names of aryl groups followed by the word imine or as nitrogen substituted primary amines. Side chain aromatic amines. Salt of amines. These are named by replacing the word amine by ammonium or replacing the word aniline by anilinium and then adding as a separate word named as anion. For example, methyl ammonium chloride, diethyl ammonium acetate, aniline bromide. Preparation of amines. First, reduction of nitro compounds. The nitro group can be easily reduced to an amino group either by catalytic hydrogenation or by chemical reduction. This method is commonly used for the preparation of primary aromatic amines. Since aromatic nitro compounds are readily available in recent years, the method is becoming more increasingly important for preparing aliphatic amines. Catalytic hydrogenation. It is generally carried out by treating the nitro compound with molecular hydrogen in the presence of finely divided nickel or platinum. But a serious limitation of catalytic hydrogen is that other reducible groups such as ethylenic double bond is present in nitro compounds also get reduced. Chemical reduction of nitro compound is usually brought about by adding hydrochloric acid to a mixture of nitro compounds and a metal such as granulated tin or iron. The amine is obtained in the form of its salt, from which the free amine is recovered by the addition of alkali followed by stream distillation. Reduction of nitriles. Aliphatic and arar alkyl primary amines can be obtained conveniently by the reduction of nitriles. The reduction may be brought about catalytic hydrogenation or by chemical reducing agents. The chemical reducing agents may be sodium and alcohol Mendes reaction or lithium aluminum hydride, which is LiAlH4. Nitriles themselves can readily got from alkyl or ara-alkyl halides by reaction with sodium or potassium cyanide. Third, reduction of oximes and amides. So reduction of oximes obtained from aldehydes and ketones by reaction with hydroxyl amines, and amides gives primary amines in good yields. The reduction may be brought about chemically or catalytically. Fourth, Gabriel phthalimide reaction. This is an important method for the preparation of pure aliphatic and ara-alkyl primary amines. Phthalimide contains an imino group flanked by two carbonyl groups so that hydrogen of imino group is acidic. Therefore, phthalimide can be easily converted into potassium salt by treatment with alcoholic potassium hydroxide. Fifth, Hoffman bromamide reaction. When treated with bromine or chlorine in an alkyl solution, an amide forms an amine containing one carbon atom less than starting amide. Mechanism. The mechanism of the reaction has been the subject of much study as it involves a rearrangement in the structure of a molecule. The hypobromite ion OBr generated by alkaline solution of bromine initiates the attack on the amide ion, which is followed by other steps also. Evidence in favor of mechanism. The above mechanism is strongly supported by the fact that the intermediates postulated in the steps 1, 2, and 3 can be actually isolated under suitable conditions. These intermediates yields the expected products of Hoffman degradation on further treatment. Sixth, reductive amination of aldehydes and ketones. Many aldehydes and ketones change into primary amines on reaction with hydrogen and ammonia at a room temperature of 373 Kelvin and 150 atm pressure in the presence of a catalyst such as nickel, and this reaction is known as reductive amination. Mechanism. Reductive amination involves the formation of amine C double bond NH as intermediate and proceeds through the following mechanism. Like ammonia, primary amines can also react with aldehydes or ketones to yield secondary amines. Seventh, reaction of alkyl halides with ammonium, ammonolysis, Hoffman methods. It may be noted through first, even through ammonolysis of halides yields a mixture of products. Primary amines can be obtained as the predominant product by using large excess of ammonia. Second, in place of ammonia, if the initial reaction is brought about between alkyl halide and a large excess of primary amine ammoniolysis reaction, the main product formed is a secondary amine. Third, similarly, ammoniolysis of alkyl halide with excess of secondary amine yields many tertiary amines. Limitations of the reaction. Reaction of ammonia with halides suffers from some limitations that described. First, the main disadvantages is that the reaction leads to the formation of a mixture of amine. As already explained, the separation of the two mixture into the individual amines is not easily. Second, the reaction takes place readily with alkyl aryl halides also. Eighth, ammonolysis of alcohols. When a mixture of an alcohol and an ammonia is heated to about 630 Kelvin in a sealed tube in the presence of copper, chromite or alumina catalyst, a mixture of primary, secondary and tertiary amines is obtained. Use of a large excess of ammonia leads to the formation of primary amines. Curtius rearrangement. In this reaction, an acyl azide obtained by reaction between an acyl halide and sodium azide is heated as in inert solution. As a result, acyl halide eliminates a molecule of nitrogen along with simultaneous rearrangement to form alkyl isocyanate, which upon hydrolysis gives a primary amine. Smidged rearrangement. This is a modified form of above reaction. Here the acyl azide obtained by reaction between the carboxylic acid and hydrozoic acid, which is HN3. In the presence of concentrated sulfuric acid, the acyl azide is allowed to undergo further reaction in with actually isolating it. RC double bond OH plus HN3 in the presence of H positive RC double bond O N3 heat RN double bond C double bond O H2O RNH2 plus CO2. Reduction of N alkyl amide and N disubstituted amides. Catalytic chemical reduction of N alkyl amides gives rise to secondary amines. N-alkyl amides, which is RC double bond O NHR, in the presence of lithium aluminium hydride and acidic medium, it will give secondary amine, which is RCH2 NHR dash. Hydrolysis of p-nitro dialkyl aniline. A very suitable method for the preparation of secondary amines is to carry out the hydrolysis of p-nitro disodyl alkyl is itself obtained from aniline. Secondary amines to carry out the hydrolysis of p-nitrosodyl alkyl aniline. P-nitro aniline is itself from aniline by N and dialkylation followed by reaction with nitrous acid. 12th, decomposition of quaternary ammonium hydroxide. The best method for preparing tertiary amines is by decomposing quaternary ammonium salts by hydrolysis with moist silver oxide. Separation of primary, secondary and tertiary amines. As described above, certain methods of preparation of amines leads to the formation of a mixture of primary, secondary and tertiary amines and quaternary ammonium salts. When the mixture of amines and quaternary ammonium salt is to be separated, it is first distilled with potassium hydroxide. The quaternary ammonium salt, being non-volatile, is left behind while the mixture of amines distills over. First, fractional distillation. This method is generally employed on an industrial scale. The mixture of amines is fractional distilled by employing highly efficient fractioning apparatus. Second, Hoffman method. The mixture of amines is treated with diethyl oxalate. When the primary amines forms a substituted oxamide, a solid, the secondary amines form dialkyl ester liquid, and the tertiary amine doesn't react. Regeneration of amines. On distilling the reaction mixture, the tertiary amines distills over first and is collected as the distillate. The remaining mixture is cooled and filtered. When oxime ester passes as the filtrate and oxamide is left as residue. Oxamide and oxamic acids are now separately boiled with alkali to get back the original amines. Hinsberg's method. This mixture of amines is treated with p-toluene phenol chloride, also known as tosyl chloride TSL, or Hinsberg reagent. In the presence of sodium hydroxide, the primary amine forms monoalkyl sulfonamide, which dissolves in sodium hydroxide with the formation of sodium salt. The secondary amines form dialkali sulfonamide, which is insoluble in alkali. The tertiary amine doesn't react at all. Regeneration of amine. The alkaline mixture obtained above is extracted with ether when the unreacted tertiary amine and sulfonamide of secondary amine passes into ether layer, while the sodium salt of sulfonamide or primary amine reacts in aqueous layer. Chemical properties of amine. The basic chemical properties of amine closely resembles those of ammonia and are largely determined by the presence of lone pairs of electrons on the nitrogen atom. The first is basic character. Like ammonia, all the classes of amines have a lone pair of electrons on the nitrogen atom. Since these pair of electrons is available for sharing for being shared by other atom which may be electron poor, amine act as bases. As such, they undergo the following reactions. Formation of hydroxide. Like ammonia, the water-soluble amines form substituted ammonium hydroxide which ionize to furnish hydroxyl ions. Formation of salt. Being basic in nature, amines reacts with acids to form salts called as amine salts. All the amines are weaker bases than hydroxide ions. Their salts are readily converted back into free amines by aqueous hydroxides. Reaction with metal ion. Due to the availability of lone pair of electrons of nitrogen atom. Amines also act as ligands to form soluble coordination complexes with transition ions such as Ag positive and Cu2 positive. For example, silver chloride dissolves in methylamine to form a soluble complex. Similarly, ethylamine reacts with copper salts to form a deep blue colored complex. Third, alkylation. All the classes of amines undergo alkylation on treatment with alkyl halides. The starting amine first changes into amine of next higher class, which ultimately changes into a quaternary ammonium halide. This process of converting an amine into quaternary ammonium salt through reaction with alkyl halide is often referred to as exhaustive alkylation. If the halide used in the some methyl halide uses, this process is exhaustive methylation. Conversion into amines, acylation. Primary and secondary amines, but not tertiary amines, react with acid chlorides or acid anhydrides to give unsubstituted amides. The reaction is referred as alkylation of amines. In the case the amine or the acid chloride or anhydride is aromatic, the reaction is generally carried out in the presence of base such as aqueous sodium hydroxide or pyridine. It is called Sosten-Baumann reaction. Mechanism. The mechanism of the reaction involves the initial addition of nucleophilic nitrogen of the amine to the acyl carbon. This is followed by the elimination of Cl negative ion and H positive ion to form substituted amines. The process of acylation is often employed for the identification of primary or secondary amines. This is because the acylation derivatives, particularly acetyl or benzoyl derivatives, are used. Conversion into sulfonamide. Primary and secondary amides also react with sulfonyl chlorides such as benzene sulfonyl chloride, which is Heisenberg's reagent, and p-taulicin sulfonyl chloride to form substituted sulfonamides. Reaction with nitrous acids. The three classes of amines react differently with nitrous acids, which is generally obtained in situ by the action of mineral acid on sodium nitrite. First, primary aromatic amines react with nitrous acid in the cold to yield diazonium salts. Reaction is known as diazotization. Primary aliphatic amines also react with cold nitrous acid to yield diazonium salts, but aliphatic diazonium salts are even unstable in the cold and decompose as soon as they are formed to yield a complex mixture of different products. Seventh, carbyl amine reaction. When a primary amine is warmed with chloroform and alcoholic potash, an alkyl isocyanide or carbyl amine is formed, which gives a very offensive smell. Since the reaction is not given by secondary and tertiary amines, it is used for distinguishing primary amines from other classes of amines. Action of carbon disulfide. When warmed with CS2 in the presence of mercury chloride, aliphatic primary amines yield isothiocyanate, which smells like mustard oil. This reaction is known as Hofmann mustard oil reaction and can be used for the identification of primary amines. On the other hand, when an aromatic primary amine such as aniline is heated with CS2 and solid KOH, it gives NN diphenylurea, which forms phenyl cyanide on reaction with concentrated HCl. Reaction with aldehydes and ketones. Primary amines react with aldehydes and ketones to form amines known as Skitch base or ethylenes. Secondary amines react with aldehydes and ketones containing alpha hydrogen atom to form carbonyl amines, which are highly unstable and readily undergo dehydration to form aniamines. Acidic nature. Even though amines are essential basic in nature, primary and secondary amine can also behave as acid when reactive with alkali metals or Grignard reagent. Tertiary amines don't undergo these reactions because they don't contain any hydrogen attached to nitrogen. Oxidation. All classes of amines are readily oxidized, but the nature of the product formed depends upon the starting amine and the oxidizing agent. The oxidation can be brought about by a variety of oxidizing agents such as H2O2, which is peroxy acid, and caro acid, which is H2SO5. Primary and secondary aliphatic amines usually give complex mixture complex mixture on oxidation, but tertiary amines are cleanly oxidized to tertiary amine oxide. In case of aryl amines, the oxidation is not confined to amino group but also takes place in the ring. Electrophilic aromatic substitution in aryl amines. In addition to chemical properties of the amino group discussed above, the ring of aryl amines can undergo typical electrophilic aromatic substitution reactions which involve carbocations as intermediates. In this reaction, the NH2, NHR, NR2 group act as strongly activating and ortho-para directing groups. This is because the pair of unshared electrons on nitrogen of these groups enables these groups to donate electrons by resonance. During electrophilic aromatic substitution of benzene itself, the carbocation intermediate formed by attacking on electrophile is a resonance hybrid of three contributing structures. Protection of amino group. It is sometimes necessary to decrease the speed of reaction or prevent the formation of side product by acetylation of the amino group before introducing a substituent into the ring. The silated amino group, which is NHCOCH3, is also activating and ortho-para directing, but much less powerful than the free amino group. This is due to the fact that oxygen of the carbonyl group tends to withdraw the unshared pair of electrons of nitrogen towards itself and thus make the pair less available for the donation of the aromatic ring. Halogenation of aromatic amines proceeds at a very fast rate and all the available ortho and para positions get halogenated. Nitration. Direct nitration of aromatic amines is not a feasible reaction due to following reason. Direct nitration results in the formation of oxidation products in the desired nitro compounds. Even though amino is ortho-para directing, direct nitration results in the formation of mixture of meta and para derivatives. Sulfonation. In spite of the presence of strongly activating amino group, the sulfonation of aromatic amines takes place under rather drastic conditions. For instance, aniline gets sulfonated only when heated at 453 to 463 Kelvin for 4 to 5 hours with concentrated sulfuric acid and is commonly known as sulfonilic acid by the main product. Aliphatic amines. Greatly basicity of aliphatic amines as compared to ammonia. First, inductive effect. The greater basicity of aliphatic amines as compared to ammonia can be explained in terms of electron releasing inductive effect of alkyl group. Aliphatic amines contain one or more alkyl group in place of hydrogen atoms of ammonia. Now an alkyl group being nitrogen being electron releasing increases the electron density on nitrogen and thus make the electron pair on nitrogen more freely available. It may be noted that due to inductive effect alone, a tertiary amine should be more basic than a secondary amine, which in turn should be more basic than the primary amine. Order in the following cases. CH3 whole twice NH is more basic than CH3, NH2 then more basic than CH3 whole thrice N. This means that relative basicity of primary, secondary and tertiary amines can't be explained in terms of electronic factors alone. There are other factors, particularly solvation effect, which also play an important role as explained below. Solvation effect. This is another factor which strongly influences the basicity of amines in aqueous solution. The substituted ammonium ions formed by amines by taking up a proton are highly solvated in water through hydrogen bonding and are therefore strongly stabilized. As such, the basicity of amines should decrease corresponding. It is therefore apparent that inductive effect and solvation effect have opposing influence on the basicity of aliphatic amines. Aromatic amines. Weaker basis character of aromatic amines as compared to ammonia. To understand as to why aromatic amines are weaker bases than aliphatic amines or ammonia, let us have a look. It is evident that aniline is a resonance hybrid of 5 contributing structures. In 3 of the contributing structures, the electron pairs on nitrogen is shared with aromatic rings and thus less available for sharing a proton. Effect of substituent on the basicity of aromatic. The basicity of aromatic amines is greatly influenced by nature as well as position of the substituent present on the benzene ring. The nature of the group determines the inductive effect, whether plus I or minus I, and its resonance effect, whether plus R or minus R or minus R or plus R. The position of the group determines its net effect on the electron density of on nitrogen. Substituents having an overall electron releasing effect such as CH3, OCH3, NH2 tend to increase the basicity. On the other hand, overall electron withdrawing groups such as minus X, which is a common for halogens, NO2 tends to decrease the basicity. All groups, whether electron releasing or withdrawing, decreases the basic strength when present in ortho position. At the same time, electron withdrawing group exert maximum base weakening effect when present in ortho position, and this is known as ortho effect. For example, while P and M toluenes are stronger bases than aniline, O toluene is a weaker base than aniline. Some important observation. First, electron releasing groups exert greater base strengthening effect when present in para position than when present in meta position. This is because such group increases the electron density at nitrogen to a greater extent when present at para position. Second, electron withdrawing group usually exert greater base weakening effect when present in para position than when present in meta position. For example, P nitroaniline pKb is 13, M nitroaniline pKb is 11.5, aniline pKb is 9.387, and here more basic is aniline, then second is M nitroaniline, and third is P nitroaniline. Third, halogens such as chlorine, bromine exert greater base weakening effect when present in meta position than when present in para position. For example, basic strength of meta and para chloroanilines are as follows. More basic is aniline, then P chloroaniline, and then M chloroaniline. Fourth, the case of certain groups like OCH3, OH is peculiar. They act as base strengthening when present in para position but base weakening when present in meta position. For example, more basic is P methoxy aniline, and then aniline, and then M methoxy aniline, because of the inductive effect, which is minus R, electron withdrawing, and electron releasing resonant plus R effect. When OCH3 group is present at meta position, it can exert only minus I, since resonance effect doesn't operate at meta position. This decreases the electron density at nitrogen, so M-methoxyaniline is a weaker base than aniline. So that as a comparison of influence of various groups on the acidities of carboxylic acid and basicity of amines shows that a substituent which increases the basicity of an amine decreases the acidity of carboxylic acids and vice versa. This is not surprising because a group which can stabilize a positive ion formed by the amine by dispersal of the positive charge would naturally destabilize a carboxylate ion by intensifying its negative and vice versa. That's all about our chapter amine. Thank you.